Alright guys, so this is the second video of sections 2.1/2.2. So if you haven't watched the first video, please make sure you do that first. Alright, so in this video, the first thing we're going to do is go over biconditional statements. Okay, so biconditional statement is when a conditional statement and converse are both true. Okay, that's the only time that you can write something as a biconditional statement. Okay, and when they are, you can put them together to write them as a biconditional statement. Okay, so a biconditional statement is a statement that contains the phrase if and only if, and we'll do plenty of examples. Okay, now when we write it, remember we wrote P arrow Q? Well, this one's P with a double arrow Q. Okay, so anytime you see this, it's P if and only if Q. Okay, now there's no if at the beginning and no then in the middle. It's just if and only if in the middle. And then once again, your P is the hypothesis and your Q is the conclusion. Guys, any good definition always be written as a biconditional statement. So if I ask you on a test to write a biconditional statement, think of a definition, and that's probably the easiest way to come up with one. All right, so let's look at the first part of example A. Okay, so it says rewrite the definition of perpendicular lines as a biconditional statement. Okay, so they have it as a conditional statement here. It says if two lines intersect to form a right angle, then they are perpendicular. Okay, well, you don't have to do this every time, but I just want to show you. Okay, if we write the converse of this, remember the converse is when we flip the hypothesis and the conclusion. So the converse would be if lines are perpendicular, then they, can't spell, intersect to form a right angle. Okay, now read both of these. If two lines intersect to form a right angle, then they are perpendicular. That is a true statement. That is the definition of what perpendicular lines are. Okay, now if you read the converse, it says if lines are perpendicular, then they intersect to form a right angle, which is also a true statement. Okay, now because both of these statements are true, we could write this as a biconditional statement. So the biconditional statement would say two lines intersect to form a right angle, and this is what makes it a biconditional statement. If and only if, here's the keywords right here, if and only if they are perpendicular. Okay, so this would be a biconditional statement. Notice there's not an if at the beginning and there's not a then in the middle. It's just if and only if together in the middle that ties those hypothesis and conclusions together. All right, let's look at B now. Okay, so it says rewrite the definition of complementary angles as a biconditional. Hopefully you know what complementary angles are. But as a conditional statement, it says if two angles are complementary angles, then they sum to 90 degrees. Okay, now if we wanted to write the converse, I'm not going to write the converse of all these, but if we wanted to write the converse, it would be if the sum of their measures is 90 degrees, then they are complementary angles, which is also a true statement. Okay, so because both the conditional and the converse are both true, I can write it as a biconditional statement, which says two angles are complementary. And then once again, here's the kicker, if and only if, those are the key words, if and only if they sum to 90 degrees. Okay, that is my biconditional statement. All right, so I want you to do is I want you to pause this video. Okay, and then I want you to write C, D, and E as a biconditional statement. And when you're done, unpause it and we'll go over them. All right, so hopefully you tried to do all three. I'm going to go over the one and then explain D and E in a little more detail because it's a little bit more confusing. So C was pretty basic. It says an angle is a right angle if and only if it measures 90 degrees. That should have been the biconditional statement. Okay, now notice on D and E, we have actually two conditional statements put together. Okay, so D said, if Mary is taking a theater class, then she will be in the fall play. Okay, then the next section says, if she will be in the fall play, then she must be taking a theater class. Okay, now those are the same, it's just the conditional and the converse, because the only thing is flipped. So just because you have two statements, it still operates the same way. So we can write the biconditional is Mary is taking theater class if and only if she is in the fall play. Okay, the only difference is they wrote the converse too. So if you can run for president, then you're at least 35 years old. Okay, and then the converse of that is if you're at least 35 years old, then you can run for president. So hopefully you wrote the biconditional as you can run for president if and only if, keywords, you are at least 35 years old. All right, last thing we're going to do is talk about counterexamples. Now, counterexamples are pretty darn important. Okay, so first of all, to show that a conjecture is true, you must show that it is true for all cases. So in math, if we say a statement is true, that means it's true all of the time. If we can find one case of when it's not, we consider it a false statement. Okay, so to show that a conjecture is false, you must find just one counterexample. Okay, now a counterexample is just like what it sounds, is a specific case for when the conjecture is false. So we want to find one example of when a statement is false and it makes the whole entire statement false. Okay, so our goal is to find one example of when it is false. All right, so if I look at A, it says a student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. Now, when I ask you to find a counterexample, don't tell me the statement is false, okay? Because I know it is false, which is why we can find a counterexample. So what I'm looking for is one example of when the statement is false. Just one example. Okay, so here's the statement here. He says, the sum of two numbers is always more than the greater number. Okay, now you have to read this a couple times. The sum of two numbers is always more than the greater number. So if I add two numbers, their sum is going to be bigger than the bigger of the two numbers. Okay, so think about this. If I add 1 plus 0, okay, 1 plus 0 is 1. Now, is this one bigger than the larger of these two numbers? Well, the larger of these two numbers is 1, and 1 is not bigger than 1, it's equal to it. So this would be one counterexample. Okay, so I want you to think to see if you can think of another counterexample. Okay, now we could also throw in negative numbers here. So like what if negative 2 plus 1 is negative 1? Okay, is negative 1 bigger than the bigger of these two numbers? Well, the bigger of these two numbers is 1. Is negative 1 bigger than 1? No, it is not. So this would be another counterexample, okay? A lot of times you can find more than one counterexample. All right, I want you to pause this video and I want you to try to find a counterexample of B and C, and then we'll go over them. So go ahead and pause this, work through B and C, and then hit the play button again, we'll go over it. All right, so let's look at B now, okay? The value of x squared is always greater than the value of x, okay? So anytime I take a number and I square it, the number we get is gonna be bigger than the number we square. Okay, well, look at 1 squared. Okay, so this one here, our product or the value of the square is not bigger than this number. It's the same. So that makes this statement false. Okay, another example would be 0 squared. Well, 0 squared is 0. Okay, well, this 0 is not bigger than this 0. So that would also work as well. And then the last thing I could think of, and there may be more, guys, is anytime that you square a fraction that's less than 1 or a decimal less than 1 even, okay, this number is going to be smaller than this number. Anytime you square a number less than 1, it's going to be smaller than this number. Okay, and on C it says if two angles are complementary, remember complementary means they add to 90, then they are not congruent. Okay, so what I want to do is find a time when I have two complementary angles and they are congruent. Well, that can happen if both of these are 45 degrees. So if I have both of these are 45-degree angles, these are complementary and they are congruent, so this would be a counterexample as well.